Alright, so here's the Minecraft lever. It's the same as the old version, even including the horizontal pins. The only difference is the model on the right is optimized. Previously on the left, it had no ridges. On the right side, you're able to open it up and also closing it just by pressing it into place. And everything gets locked in, it doesn't push out, and you don't have to weld the plastic together or melt the plastic together. Also in the old version, it used a pin. This metal pin was from a rivet that I cut off and just used it in this model here. In order to simplify the construction, I made the inside radius that holds the rod smaller in order to account for the 1.75 filament. As long as it has a radius of 1.75 millimeters, you can just fit it through the lever, push the lever through and into those guides, and now you have your lever. Here's the base. It just uses copper foil tape as well as 2 metal leads that are poked through the bottom. I layered another piece of copper tape and soldered that piece onto the piece underneath, as well as soldering the lead straight onto the copper foil tape. The leads fit horizontal. In this earlier revision, I had these vertical, but I swapped it over to horizontal in order to accommodate for the later redstone design. So on this side, it'll be data in, and then on the other face, it will actually be data out. And on this face, it'd be data out on the right side. And on the other face, it would be data in. Finally, just like the old version, it just has a thin piece of copper foil tape here on the edge. And if it doesn't make good contact, you can just layer as much copper foil tape on top of each other. There also is a slight detent that's created. And so now with the new lever, it's more secure. The rendition isn't completely perfect. As you can see, if I press it all the way down, then it turns off, but then turns on again once I completely put it down. And this is due to the contact not being just right. Here's a 3D model. At its limit, it sits flush against the base. There's a bit that bumps past the body. The bump serves as a detention or a detent. It also gives a tactile feedback when switched. When printing, the tolerances aren't as tight, so there's a gap that ends up between the base and the lever arm. In order to avoid this problem, you can just add more copper foil tape to the lever hand. By putting more tape, you increase the force of the lever arm against the base, making a more secure connection between them. So the lever arm is pretty useful since you can just flip it over to invert a signal. Here you can have the correct configuration for the redstone torch, where if you activate the lever, it turns the torch off. Then by flipping the lever again, and it turns the torch back on by default. Unlike with the button where it will only activate once you press it. And so if I press the button, it'll turn the torch on, and then let go of the button, turns the torch off. In order to fix this issue, it just takes a little bit of rewiring. And so right here is the 1000 ohm resistor, since it's being powered by 5 volts. This is just limiting the current so that the LED doesn't burn out. Instead of the resistor being pulled down to ground, this time it's connected to the positive and connected to the positive rail of the voltage. Here I'll be adding a button over to a wire. So now this green wire is connected to the positive end of this LED, and the right lead of the button is connected directly to ground. Now when I press the button, the LED will turn off. If I let go, the LED will turn back on. The resistor is acting as a current limiting resistor, supplying voltage to the LED. By pressing the button, you're just connecting the positive lead of the LED straight to ground. Since there's a voltage potential of 0 on the positive end of the lead and 0 on the negative side of the LED, no current is able to flow through the LED. Now, one thing to keep in mind is that current is still flowing through this resistor even if you press the button. Since by pressing the button, you're basically just connecting the other side of this resistor down to ground, removing the voltage potential here completely. If you're using small value resistors below 1000, I don't recommend using this configuration, since when you connect that resistor down to ground, it'll allow too much current to run through that resistor, burning it up, and could lead to a fire. So be careful on what resistor you're using, as well as how much voltage you're supplying. So here's a simple circuit. You have the positive 5 volts going through the resistor and through the LED and down to ground here. When this button gets connected, then it'll short this wire here, and so the 1000 ohms will be directly connected to the ground. That'll result in everything after this 1000 ohms to be a voltage potential of 0, since it's directly connected to the ground. Current will still be able to flow through this 1000 ohm resistor, since when the button closes, it completes a circuit. When the button is left open, it's still a complete circuit. However, this time the current is able to flow through this LED and down to ground. In order to extend this output to more LEDs, you could connect them in parallel, but when you connect in parallel, you end up with a lower brightness or also less current running through the LEDs. In order to fix this, you can grab a signal from the right side of this resistor and the positive end of the LED, connect it to a MOSFET. From that MOSFET, you can connect an array of LEDs. Each of these LEDs represents a redstone dust. I'll be going over this array in more detail in a redstone dust video. It's basically just using Schottky diodes with the LED connected to a resistor. You can see if I press the button, the whole array turns off. When the redstone torch turns off over here, or this LED turns off over here, and it turns back on when this redstone torch turns back on. A pull down resistor is not needed between the gate and ground, since when the button is pushed, the gate already gets connected down to ground through this line and will clear the voltage potential inside the MOSFET. The downside is you need to have the ground of the LED array connected to the source of the MOSFET. That means if you wanted to power these when they're on-off state, you need to use another MOSFET in order to ground the circuit. Since it's only waiting for a ground potential, that means over here at the beginning there will always be a 5-volt potential here. And so if it was redstone dust and we wanted to only send a signal this way, you would be able to apply a different voltage, but this initial voltage when the button is not pressed will remain constant. So that means when you connect ground, not only will this side begin with 5 volts and go down this way, but there will still remain this 5 volt over here that will go down this way. Even if the button is pressed, it will still remain 5 volts on this side and 5 volts on this side since they share the common ground. So instead of using an NPN transistor, you would need a PNP transistor instead. And so that way, instead of connecting the ground potential, you'd actually be supplying power instead. So that's pretty much it. If you have any questions, please let me know. And thank you for watching.